Welcome back to Engineering Tech Tutor, the online resource for student and graduate engineers. In episode 2, we'll be looking at simple stress and strain. So before we begin, let's go back to episode 1 and just quickly recap. So in episode 1 we looked at tensile and compressive loads, those that push and pull a material apart. Although we didn't actually cover it in episode 1, we should have said that these are called direct stress and strain. Now, what do we remember? Well, stress is a measure of pressure. It's measured in pascals, and its unit, when we write it down, is sigma. The equation for stress is force over area. Strain is a measure of elongation. It's unitless because it is a ratio of lengths. Its unit, when we write it down, is epsilon. The equation for strain is delta length over the original length. And when we want to calculate with either of these, we need to connect them with a variable called Young's modulus. It is also measured in pascals. Its unit is E. The equation for Young's modulus is stress over strain. Okay, so let's now look at a slightly different scenario. We've got the bar on the screen. Let's imagine we grip it in our hands. If our left hand stays still, but we pull our right hand down, we exert a thing called a shear stress. Between our hands, the piece of material is pulled in two different directions. One half wants to stay where it is, and the other half wants to move vertically downwards. At that area where that is happening, which I've shown here as a hatched area, the material is under a load called shear loading. So if we have forces acting perpendicular to the material, these are known as shear. Okay, let's apply that shear force onto the bar once again. Now, remember before, stress is force over area. Well, in the case of shear stress, the area is the cross-section of the material. The symbol for shear stress is tau, and shear stress is measured in pascals. Don't forget, 1 pascal is 1 newton per square metre. And if you're ever doing the calculations, as I suggested in the first episode, don't forget to convert your area into square metres. It may be given to you in different units, always be cautious. The equation for shear stress, tau, is force over area. Should we do an example? I think we should. Okay, so a 6 kilonewton load is applied to a 20mm diameter peg that is fixed at one end into a block. What is the shear stress in the peg where it is connected to the block? Okay, so fairly typical question you'd find in most science papers. So how are we going to work this one out? Well, let's work through it. First of all, we need to calculate the area of the peg. So we know it has a diameter of 20mm, and we'll use the standard equation for an area of a circle, which is pi r squared. So we take the diameter, we need a radius, so we'll divide it by 2, and we need to convert it into meters, so that works out at 0.02 meters divided by 2. We'll square it and we'll multiply it by pi. That gives us an area of the pin of 0.000314 meters squared. Okay, now stress is force over area, and so what we're going to have to do now is take the force of 6,000 newtons or 6 kilonewtons and divide it by that area we just calculated. When we do that, that gives us a shear stress of 19,108,208 pascals, or to give it a slightly more usable unit, 19.1 megapascals. 1 megapascal is 10 to the 6 pascals, so it's a much more efficient way of writing a large number. Okay, so when we looked at direct strain, we remember that strain is a measure of stretch or elongation. If I apply a shear load to the bar, then at the interface, at that surface between the two forces, we'll see a deformation, but it's not the same as direct strain. Let's think of it like this. We have this orange rectangle. If I hold the left-hand side of it and I apply a force to the right-hand side, we will pull it down on the right-hand side, and it will look like this. It'll become a parallelogram, and we can say that the sides of it have an angle. That angle is the shear strain. So shear strain is the angle of deformation. The symbol for shear strain is phi, and it's measured in radians. Radians are an angle, a bit like degrees, but it's just a different unit. If you want to convert between the two, all you need to remember is that 2 pi radians is 360 degrees, or 1 pi radian, or pi radians, is 180 degrees. It's fairly usual to use radians in engineering, so it's probably worth to remember that one. Okay, so do you remember Hooke's law from the first video? Well, we said that if we apply a load to a material, it stretches, and if I increase the load, then the amount of stretch increases, and that those two remain proportional and up to a point. That was the limit of proportionality. And whilst that was happening, whilst they were proportional, that was known as Hooke's law. And we also sort of decided that there was a relationship which was known as Young's modulus, which was E. Well, the same thing happens now in shear stress and shear strain, except we don't call it Young's modulus, we call it shear modulus, or the modulus of rigidity, and we don't give it the symbol of E anymore, we give it the symbol of G. Other than that, it's pretty much the same. If you remember from the first episode, you've probably got it sorted now for this. You don't need to remember much else. Just remember it's G, not E. And modulus is still measured in pascals. So shear modulus is the shear stress tau over the shear strain phi. Well, that's the basics of shear stress and strain. I hope you enjoyed it. I must admit it's not probably the most exciting of topics, but in the next episode we'll go a little bit more into Hooke's law and what happens when you go past the point of proportionality. Don't forget to like the video and to subscribe to our channel. Thanks very much. See you next time.